Good afternoon and evening from wherever you're tuning in. My name is Ryan White. I'm the director of Morrison Planetarium, and you are seeing live footage from Morrison Planetarium, but we do have a slight audio problem. We're going to be looking to fix that, but otherwise you can expect me to come on board and narrate what we're seeing in just a moment. We are looking into a technical difficulty that's preventing us from hearing what's going on in Morrison Planetarium, but you are seeing visuals streamed live from Morrison Planetarium in San Francisco. Mary Holt is actually presenting a presentation in the dome right now. She's a specialist, planetarium program specialist at the California Academy of Sciences, and so we're watching her pilot through the universe. Unfortunately, her audio is not being directed here to YouTube or Facebook. So I'm going to try to narrate what we're seeing. We're actually looking out at a portion of the Milky Way right now, and we are currently approaching Earth's moon. Now, it's worth noting that this is as far as humans have traveled out to space, and during the next 20 to 30 minutes, we're actually going to be making a trip through a virtual universe that is collected from data that has been assembled by planetary scientists and geologists and astronomers over the past several decades. So as we orbit the moon, we're actually seeing satellite imagery that has been pieced together from multiple missions to the moon. And that data has been collected into our Digital Universe Atlas, and we're actually seeing the output from a program called OpenSpace. We'll be sharing some links to our OpenSpace software in chat, but one of the things that is amazing about this is that we can break the laws of physics. We can travel faster than the speed of light, and we can go to various virtual destinations in our planetarium software. So again, what you're seeing is actually just a small part of what's projected on the dome here in San Francisco. And as we orbit the moon, you can actually see the darker regions, which are called mare. Those are kind of a darker lava, and directly in front of us, you can see lava that sort of filled in one of the craters. And as we pull away from the moon, again, I'm going to be narrating as Mary does the piloting, so I'll do my best to describe where we're going, except that I kind of won't know until we get there. So as we pull away, we can actually see the orbit of Earth's moon around Earth. So Earth just kind of entered from the very top of the frame there. And we can see the trajectory of Earth, its Earth's orbit around the sun. And what's worth noting is that the radius of that orbit, so that tiny circle which is diminishing in front of us, is about 400,000 kilometers, about 240,000 miles. And it's a distance that light travels in just about a second and a half. Now, the sun, which just entered from the left, is a lot farther away. It's closer to 93 million miles, 150 million kilometers. And the distance between the sun and Earth is more like 8.5 minutes in terms of light travel time. So now what we're seeing is the sun here at the center of our image and the orbits of the four inner planets, Mercury, Venus, Earth, and Mars, relatively close by. And then in the distance over on the left, you can see Jupiter. The orbit of Jupiter is a lot farther out than the planets of the inner solar system, but those inner planets are relatively close to the sun and beneficiaries of its light and heat. As we pull farther away, actually, it looks like that's the orbit of Jupiter. So the line that we see in the distance is actually the orbit of Saturn, and I'll expect that we'll see Uranus and Neptune coming into view now. These are the orbits of the 8 planets in our solar system. And now, if you look at from the top of the image to the bottom in terms of the solar system scale, it takes light about 8 hours to traverse the diameter of our solar system. So if you think about that, the second and a half in terms of light travel time, that's the distance from Earth to the moon, is maybe like a brief pause in conversation. 8.5 minutes from the sun to Earth is more like maybe a quick lunch. And 8 hours is like a good night's sleep. And the brighter orbit that you see, a little farther out than the orbit of Neptune, is the trajectory of Pluto, the orbit of Pluto around the sun. Now, Pluto may have been reclassified a little over a decade ago from being a planet to being a dwarf planet, but it's still an interesting object in our solar system. One of many what we call Kuiper Belt objects, sort of small icy worlds that are much farther away from the light and the heat of the sun. So the vast collection of those objects is being highlighted here, including their trajectories, their orbits around the sun. And you can see it's a much more crowded field than it looks when you just see the orbit of Pluto. Now, that's one of the reasons why Pluto got reclassified a while ago, because we now know that it's not alone in the outer part of the solar system. Instead, there's a lot of stuff out there. So one of the reasons that Pluto is considered a dwarf planet is because, unlike the 8 planets in our solar system, it shares its orbit with a lot of other stuff, including the objects that you saw depicted there just a moment ago. I'm not sure exactly where we're going to go next. I'm kind of waiting to see where Mary takes us. But as we continue to sort of orbit around the solar system, you can actually see the Southern Cross in the upper right-hand corner, and just below it, 2 bright stars, including a kind of yellowish one. That's Alpha and Beta Centauri. And Alpha Centauri, the yellowish one, is actually the closest star. And while I mentioned that the solar system is about 8 light hours across, Alpha Centauri, the closest star, is more like 4 light years away. Now, for comparison, some of the additional trajectories and kind of the warmer colors that we can see here on the screen now, those are not the trajectories of planets or dwarf planets or other objects in our solar system. Those are the trajectories of 5 of the fastest spacecraft we have ever built. The Voyager 1 and 2 spacecraft, the Pioneer 10 and 11 spacecraft, and the New Horizons spacecraft are incredibly fast nuts and bolts objects that we've sent out to explore our solar system. And you can see now, if you kind of compare where they are, because we're projecting them out to their current locations in the solar system, none of them has traveled as far as light travels in a single day. Because remember, the diameter of the planet orbits there are about 8 light hours at the maximum. So when I talk about light travel time, either that 1.5 seconds from Earth to the moon, the 8 minutes from 8.5 minutes from the Earth to the sun, or the 8 light hours across the solar system, that light travel time is something that is great for observing things that are more distant, but it's a speed limit that we cannot exceed. So with our physical spacecraft, we can't exceed the speed of light. Instead, we're constrained by how fast our propulsion can take us out into the universe. And so even, and I mentioned Alpha Centauri earlier, that's the star that's now kind of in the foreground, just to the left of the sun, which is at the center of the image. Even the distance to the nearest star is much, much farther than we can travel with our current spacecraft and our current propulsion systems. It would take about 10,000 years using our current technology to reach the nearest star, Alpha Centauri. So now, as we continue our trajectory away from home, away from Earth and the sun at the kind of center of this image, you'll see that more and more of the stars are kind of drifting away from the positions that they appear to have in our night sky. The Earth's night sky, we can recognize constellations, but now we've pulled so far away, tens of light years away, vastly exceeding the cosmic speed limit of the speed of light. And we're seeing the stars kind of shift in 3 dimensions, a little bit like traveling through the Starship Enterprise through the local star field. And although we pointed out the kind of nuts and bolts objects, those spacecraft, the 5 spacecraft that we've sent out into the universe around us, they haven't reached very far. They haven't reached as far as light travels in a single day. But this sphere that you see in front of us is what we commonly call the radiosphere. We've nicknamed the radiosphere. Now, that's the kind of outer limit of not our physical nuts and bolts objects, but of the electromagnetic radiation that we have sent out into the universe around us. We use television and radio and radar. We've exploded nuclear bombs in the past, fortunately, decades ago. But all of those create electromagnetic radiation that can leak out of our atmosphere and be observed from a great distance. That sphere that you see in front of us, kind of receding into the distance, is kind of Earth's technological footprint in the universe. It's a sphere filled with, or at least partly filled with, radiation that has been emitted by our technology. It's about 90 light years in radius, so about not quite 200 light years across. And as we pull farther and farther away from home, we'll kind of keep Earth at the center of our image as we pull away. We'll see the scale of that electromagnetic footprint of humanity and the universe around us relative to the size of our galaxy. Now, all of those stars that we saw relatively close by to home, those are all part of our own Milky Way Galaxy. And off to the right of the image, you can actually see the large and small Magellan clouds, the large Magellan cloud at the top, the small Magellan cloud at the bottom. Those are two satellite galaxies of our own, but the Milky Way here at the center of the image is a collection of hundreds of billions of stars. From one side to the other is about give or take 100,000 light years. So that light travel time, that distance measurement that we've been using initially from the Earth to the moon, across the solar system to the nearest star, now we're seeing our galaxy, which in terms of light travel time is kind of comparable to the age of our species on this planet. And at the center is still our solar system surrounded by that radiosphere, that giant sphere, nearly 200 light years in diameter, is now just a few pixels on our display. That is humanity's footprint in the universe around us. But in addition to emitting light into the universe, emitting the light in the form of radio waves, we collect light. We examine light, not only from other stars in our galaxy, but from other galaxies in the universe around us. We can look out and understand that we are not alone in the sense that there are other galaxies out there, other kind of massive cities of stars with hundreds of billions of stars, or perhaps even more. And so as we pull away from our Milky Way here at the center of the image, we'll fade up some of these little dots in the background. Each one of those dots now represents an individual galaxy. Each point of light is in fact representative of hundreds of billions of stars, perhaps even a trillion stars in some cases. And this begins to reveal itself as sort of we've referred to as the large-scale structure of the universe. The universe isn't sort of uniformly filled with galaxies. Instead, they're clumped and clustered together. And you can see that as we pull farther and farther from home, now having traveled tens of millions of light years from home, that these galaxies do indeed cluster together. Kind of at the top of the image, you can see a clump of galaxies close to the center. That, I'm pretty sure, is the Virgo cluster of galaxies, the densest conglomeration of galaxies in the nearby universe. As we pull farther from home, you can see this pattern continues as we get farther and farther away. What we're seeing are collections of galaxies, again, every dot representing an individual galaxy with hundreds of billions or perhaps a trillion stars. And we've been able to tease apart the light emitted by these galaxies and measure the speed with which they're moving away from us, which has allowed us to, in turn, figure out how far away they are, because our universe is expanding. So that measurement of the redshift, or the speed of these galaxies, allows us to figure out their distances. And so we can create this three-dimensional map of the universe, this three-dimensional map of the large-scale structure of the universe. Now, from this perspective, you can see that it kind of looks like the galaxy is sort of butterfly-shaped, and that is not the case in reality. In fact, we think that the space is sort of uniformly filled with galaxies, or filled with this kind of structure of a network of clumps and clusters of galaxies. It's just that we haven't explored the entire sky around us, and therefore the entire universe. So there are missing parts. There are gaps, kind of to the top left and the lower right. And as we continue to make measurements, continue to collect light from these distant objects, we can fill in those gaps, and we can begin to make a more complete map of the universe around us. Now, these very faint kind of reddish dots that are fading up even farther away from home, here where we are, the very center of this image, these are in fact not even galaxies. These are the bright cores of young galaxies called quasars. And what we're seeing is something that we don't see really close to home. Instead, we only see it at a great distance from us because, and I want you to think again about that light travel time concept, because light travels at a finite speed, as we look out into space, we're actually looking back into time. So these red points, these quasars, represent an epoch, an earlier epoch in the history of our universe, when the bright cores of these young galaxies burned brightly. And we can detect them at tremendous distances. These objects are perhaps even 1 billion light years away. And so this idea of looking out into space and back into time really comes to the fore when we see this kind of mottled image that we're seeing fading up in the background. This is the cosmic microwave background. And it's not an image quite like that image of, for example, the moon, where we were looking at the surface of the moon toward the beginning of the program. Instead, this image is kind of like a heat map. The dark blotches represent kind of cooler parts of the early history of the universe, because this is a baby picture of the universe, really. And the brighter spots represent hotter portions of the early universe. So this light has been traveling to us for perhaps about 13.8 billion years. It dates back to when the universe was a mere few 100,000 years old. But because the universe is about 13.8 billion years old now, this light is very old indeed. It represents what the universe looked like when the universe was very, very young. And what's interesting is that clumping and clustering, the bright clumps versus the dark clumps, represent a distribution of not only temperature, but density in the early universe. The dark parts are actually a little bit denser. The bright parts are a little bit less dense. And those eventually collapse to form the clusters of galaxies that we see close to home. So this is a really big picture. We're looking at a representation of the entire observable universe, in the sense that all of these points of light, and as we dive back down into the back toward home, toward Earth, we'll pass by those quasars, the individual points of light representing galaxies. All of these observations are observations that we've collected. We appear here at the center of this image, in the here and the now, because we're the ones plotting this data. We're the ones depicting these distances relative to us. We end up at the center because we're the ones making the picture. So now, as we dive into the local clusters of galaxies, passing by some of the clumps and clusters of galaxies are relatively near to us, we'll go ahead and approach our own Milky Way Galaxy, which appears at the center of the screen, again, because we're the ones drawing the picture, and we've kind of put ourselves at the center of this vast collection of data. And as we approach the Milky Way, we'll sort of start to fade down those individual points of light representing more distant galaxies. We'll go ahead and replace our image of the galaxy with a three-dimensional model of the Milky Way. Even though we've never traveled this far away from home in reality, we can make good, informed guesses about what our Milky Way galaxy looks like, and in fact make measurements of its structure, so that now, as we dive into the sort of tens of thousands of stars that are relatively close to home, we'll approach that radiosphere again. Again, this is the footprint of our technology in the universe around us, 200-ish diameter sphere centered on Earth that represents the radiation that we've emitted out into the universe. And as we travel by the stars relatively close to home, we'll go ahead and approach the sun. And we should soon see the orbits of the planets around the sun as well. We actually make the sun a little bit dimmer as we get closer, because if it were drawn in the same way the other stars are, it would kind of obliterate all of the details in our representation of the solar system. So now we're passing in through the orbits of the 8 planets, the trajectory of Pluto there visible in the distance, approaching the third rock from the sun, our own home planet, Earth, passing the orbit of the moon, and finally home. So again, this program has streamed live from Morrison Planetarium. You're not hearing the same person that the folks in the Morrison Planetarium are hearing. Instead, I'm kind of narrating ad hoc as we followed the piloting of Mary Holt, who gave the presentation in Morrison Planetarium. Thanks to a little bit of a glitch with our audio system, we didn't get to hear Mary directly, but I tried to do my best in terms of narrating the whole project and process and getting us from Earth out to the outer limits of space and back home. But I hope if you've had any questions, we've been keeping a close eye on chat and trying to answer the questions as they arose. And we'll also be sharing here in a moment a URL for downloading the same software that we've been using to put on this presentation, both in Morrison Planetarium and something you can run on your laptop. It's software called OpenSpace, and the OpenSpace software is freely available, open source software that you can download and play with for yourself and visit some of the same places that we saw here during the show. Go ahead and share that here on the screen. It works in both Mac and Windows, and you can do some exploring on your own, just like we're doing here in Morrison Planetarium. Thanks for tuning in today. My sincere apologies for the technical glitch. Hope you enjoyed our live stream from Morrison Planetarium. We'll look forward to doing this again next week, same time, 4:30 p.m. Pacific time on Wednesday, simulcast from Morrison Planetarium. And hopefully next week, you will also be able to hear what's happening in Morrison Planetarium. Thanks for joining us. Again, my name is Ryan Wyatt, Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences in San Francisco. We appreciate your tuning in.